Is it visible?
Yes, sir, it is visible.
Okay. So, sir, my time is up to 11 o'clock, right? 11.
Yes, sir, up to 11 you can.
Yeah. So
after 11:15, sir.
About 2 to 3 minutes before 11, I will stop so that if there are any questions.
Sure, sir.
And also, if there are any questions, post in the chat box or something like that. One of you, if you can read it out, then I will answer them.
Yes, sir, I will read it out.
Thank you.
Only if you are attending this Google Meet link, sir. Rest of the people, they are watching the YouTube live streaming.
Oh, I see. Okay.
Because there may be a lot of interruptions. Meeting.
Okay. But how is the conference going on?
Yes, sir. It's good, sir. Everything.
Okay. So, how many registered delegates are there?
Sir, total 175 paper we received.
Oh, I see.
Among that, 91 we shortlisted for the conference.
Very good.
Yesterday we finished about 50 papers.
I see.
Today going for remaining sessions.
Okay. That's very good.
Yes, sir. Professor Lakshman sir is one of the editor for this CTCS conference.
Oh, very good.
SP Dinesh from SAT Tumkur.
Okay. Yeah.
And MC Narsimhan sir is one of the editor.
Okay.
And from internal, we have Dr. Uday Kumar ji. He's in meeting.
Yeah, I'm seeing him on the screen. Yes.
He's an editor from the department.
Your voice is breaking. How about my voice? My voice is cutting.
Your voice is clear, sir. Your voice is clear. I think.
Very good. Very good.
How is it clear, sir?
Yeah, it's clear. Only when you're talking for 1 or 2 minutes, no? Then slowly it is fading off. But again, it's picking up.
Gujarat, there is little bit of voice variation. Huh?
Yeah.
Okay, sir. I will speak loudly.
Okay.
Another 1 minute start, sir.
Yeah, no hurry. I just want to make sure that I am there in time. That's all.
Thank you, sir. Thank you so much. I'll turn off my video so that I can reduce the bandwidth.
Sure.
Our HOD is there, sir.
Okay.
Dr. Dhawan Kumar. Welcome.
Yeah. Sure. Okay. Hello, Dr. Arun Kumar. How are you?
I'm fine, sir. Good morning.
Good morning.
Janakra, sir. Shall we start, sir?
That's fine with me.
With the permission of Vice Principal and HOD.
Yeah, Dr. Pujara, you can start.
Okay, sir. Thank you. So, good morning, all. Welcome for the second day of International Conference on Civil Engineering Trends and Challenges for Sustainability, CTCS 2020, under the umbrella of ICETE Multi-Conference. On behalf of Civil Engineering Department and Organizing Committee of CTCS 2020, I welcome today's keynote speaker, Dr. Nagesh Kumar D. Welcome you, sir. I also extend my welcome to our Vice Principal and Dean Academic, Professor I.R. Mitantaya. Welcome you, sir.
Thank you very much.
And our beloved HOD, Dr. Arun Kumar Bhatt.
Thank you.
I also welcome the Professor Uday Kumar ji for this keynote session. Welcome you, sir.
Thank you, Bojraj.
I welcome all the professors who are attending this particular session online, and my dear colleagues, the researcher attending the session in a YouTube link online. I welcome all of you for this particular keynote session. I, Dr. Bojaraja, Assistant Professor and Conference Secretary of Civil Engineering Department, NMAM Institute of Technology, to introduce today's keynote speaker, Professor Nagesh Kumar D. Professor Nagesh Kumar D is working in the Department of Civil Engineering, Indian Institute of Science, IISc, Bengaluru, since May 2002. He is holding the Professor Satish Dhawan Chair Professor position since October 2018. He is the chairman for Center for Earth Science IISc since March 2014. He also associate faculty in interdisciplinary Center for Water Research ICWAR and Devecha Center for Climatic Change CCC of IISc. Earlier, he worked in IIT Kharagpur during 1994 to 2002 and also worked as a scientist in Water Resources Group of National Remote Sensing Agency at NRSC Hyderabad by Cambridge University Press UK. Impact of Climate Changes on Water Resource, published by Springer, Germany, and many more. He is the editor-in-chief of H2 Open Journal by IWA Publishing UK, associate editor for ASCE Journal of Hydrologic Engineering and ISH Journal of Hydraulic Engineering. He received the Best Associate Editor Award for ASCE Journal of Hydrologic Engineering for the year 2014. He has been reviewed for more than 75 international journals. He has supervised more than 12 PhD students, 7 are in progress, and 8 postdoc, apart from many MTech and BTech theses. He received IBM Faculty Award for the year 2012 for his outstanding research in the field of modeling hydrologic extremities using microwave remote sensing. He is a fellow of Institution of Engineers India and Indian Society of Hydraulics. He is a member of the AGU, IAHR, ASCE, IAHS UK, ISMCDM USA, and Indian Society of Remote Sensing. Reviewer for more than 66 international journals and 91 Indian journals. So examiner for more than 65 PhD theses, both from India and abroad. Reviewer for many project proposals such as DST, SERB, CSIR, MOES, MOWR, MOEF, DST, NRDMS, GAN, Imprint, etc. He is also recipient of Young Scientist Project Award from Department of Science and Technology, India, under Young Scientist Scheme to conduct research on artificial neural network and their adaptability to sophisticated hydrology in 1997 to 1999. He is also a member of staff selection committee for various reputed IITs and NITs and few research organizations. He has carried out more than 1 crore worth of consultancy projects for different funding agencies. He has organized many training programs and short-term training programs. He has completed more than 21 crore worth of funded projects from various funding agencies with different investigators. I welcome you for this keynote address, sir. So may I kindly request you to present the, thank you, sir.
Thank you. Thank you, Dr. Bojraj. That's a very elaborate introduction about myself. In case if you heard too much, please bear with me and bear with his overzealousness to talk about myself. But yeah, one word is ISC. And more important is that I like the theme of this particular international conference that Dr. Bhosraj and his college team is organizing as a very apt topic. When we talk about civil engineering development, civil engineering technologies, how well they can actually meet the sustainability goals and try to help reach those sustainability goals is a very important mission by United Nations. And in that direction, I'm sure this conference will play a very important role to ensure that whatever the development that is taking place through civil engineering is actually towards sustainable development. And that's a very key issue. Um, I'm happy that the conference is going on well, and we are in the second day. And today, in the first session, I'll be talking about some of the spatial or geoinformatic tools that are found to be extremely useful for sustainable development of our society. And civil engineers have been using in various domains of civil engineering itself, like transportation, geotechnical engineering, um, water resource engineering, and environmental engineering, and to some extent even structural engineering. In all these domains, these tools are being extensively used nowadays to talk about civil engineering planning and natural resource assessment and its management using these tools. So what I will do is initially I'll talk about these tools briefly, each one of them. Then I'll try to talk about their application for water resource assessment, specifically referring to a river basin within Karnataka. Now, depending on the time available. So let's talk about, first of all, remote sensing. One of the major advantages, especially of satellite remote sensing, is that we get synaptic view of a large area in one image itself, something like this. What you are seeing here is not only India, but also its surrounding countries together put up in one digital mosaic. Okay. And you can see it's complete India, Sri Lanka, and many other countries uh, in this image itself. And that's one major advantage as far as satellite remote sensing is concerned. And trust me when I tell you that whatever you are seeing in red color in this image is actually healthy vegetation. That's because what you are seeing here is referred to in remote sensing terminology as standard false color composite. We can't see some portions of the EMR spectrum, or electromagnetic radiation spectrum, and to the portion that we can't see, we try to give some false color. So near infrared we can't see, and for near infrared red color is given, and that's how we are seeing the healthy vegetation actually in red color. I'll be referring to this again and again because some of the images that I show you, when I show them a portion of that image being in red color, it actually refers to healthy vegetation, maybe forested area or agricultural area. Now that's about the major advantage. And when we want to talk about remote sensing, some of the important characteristics that we look for are like spatial resolution, spectral resolution, radiometric resolution, and temporal resolution. I'll briefly talk about the first two, which are very important in various domains of applications in the civil engineering itself, if not in many other domains. Okay. So when you talk about spatial resolution, what we mean is just like the way you refer to in your mobile camera and all, there's a pixel. And that pixel, how much area it is covering in the photograph that it has taken. Is it 1 meter, or is it 10 meters, or is it 30 meters? Okay. So the smallest elemental area box, okay, that elemental area size is referred to as spatial resolution. So for example, a satellite may have a spatial resolution of 30 meters. It means the 30 meter by 30 meter square box on the ground will be simply seen as one dot or one pixel in the image. Therefore, if a particle, if any item is less than, let us say 5 meters or 4 meters in size, that will not be visible in that image. But any object that is larger than 30 meters will definitely be visible through that image. So we try to get images from satellites at various spatial resolutions. Just to drive the point home, I'm showing you here an image on the top left corner. It's, all these images are almost same size, but you can see that this image here is covering about 1200 kilometers of length. Okay, it's almost like square image itself, and this is through Modi's satellite. And when compared to that, if you just look at the small yellow box, that yellow box itself is this image. Okay, and this is obtained from another satellite, and here what you are covering is only 1/6 of it. That is roughly about 200 kilometers. Okay, and that is from another satellite called Landsat ETM, Enhanced Thematic Mapper Plus. Okay. And within this image, again, if you look at the small yellow box, and that yellow box itself is this image. So it is covering just about 1/10 of it, roughly, or 1 by something around that, or by 20th of it. Then you can see that it's just 11 kilometers. And within this, again, if you look at the small yellow box, that is from another satellite called Iconos. Iconos is a Greece satellite. Greece in Iconos means eye, human eye. So you can see that, depending on our interest, okay, we can try to have a large area like Ganga Basin and its surroundings or Brahmaputra in one image itself, or one portion of the basin, a tributary in one image, like you can see one tributary here. And then you can also try to see a small portion of it, let's say Benares city is somewhere, okay, and only that portion if you want to see, then it's available at a finer spatial resolution. And if you are generally interested, let's say urban hydrology, like Mangalore city or a portion of the Mangalore city, okay, then we may want to have it at a much finer spatial resolution. So typically for urban hydrology, we would like to have it at a very fine spatial resolution. For watershed hydrology, we would like to have at this resolution, and maybe for a minor river or a tributary at this resolution, and for major river basin at this resolution. So depending on our need, we can try to look for a satellite image of a specified spatial resolution. When if you are looking for, let us say, this size image or this entire area, you may have to purchase about 3,600 images. Okay. So that's the way we can try to decide what is the spatial resolution that we should look for any natural resource assessment. I repeat again, what you are seeing in red color here is actually healthy vegetation, either forested area or crop area. Now, another important aspect of the remote sensing is temporal resolution. That's, by satellite, by name of the satellite itself, it means that, we try to, the satellite rotates around Earth at regular intervals of time. And its period is typically about 100 minutes. So in about 100 minutes, it completes one revolution around Earth. And Earth would have rotated by that time. So it tries to cover the entire globe because of high frequency at which the satellite is orbiting around Earth. And that means it covers the same area again and again at regular intervals of time. And that interval is referred to as temporal resolution. For example, a satellite may take about 22 days to revisit the same place. That means it covers the entire globe in 22 days and comes back to the same location. That means for every 22 days using that satellite, we can get the image. And some other satellite may give it at 10 days, and some other satellite may give it every day, like NOAA, AVHRR, right? So depending on a satellite, we can try to get the information of a given region at regular intervals of time, which is so useful to talk about change in land use, land cover. For example, what is urban sprawl? How is urban area growing? Or what is the crop that is grown in this season when compared to the crop that is grown in the next season or previous season? Any temporal variations. And monitoring of a dynamic event like cyclone, flood, volcano, earthquake, etc. can all be done because of the temporal resolution of the satellite. So what we require is very simple. An image before and after the event will be helpful to do that. And just to drive the point home, I have displayed here the Krishna River Basin, okay, during different months within a year. So this is in Jan, this is in March by bi-monthly products. You can see Jan, March, May, July, September, and November. 6 images. Okay, and you can see that in January, only portions of the image are in red in color. Okay, especially this is Western Ghat region and some portions near Krishna Basin. I mean, at the end of the Krishna Basin, Vijayawada and other places. Okay, otherwise everything is dry. But by the time we come to September, the peak vegetation period or peak crop growing season, okay, monsoon period, you can see that most of the image is red in color, indicating that large area is under agricultural activity. And that variations over time can be easily monitored with the help of temporal resolution of the satellite. Same case, if you have an image before the flood event and image immediately after the flood events, we can talk about flood inundation, things of that kind. A very important aspect of satellite remote sensing, temporal resolution. Then the next tool is actually GIS, or Geographic Information System, which we have been using even if you don't know, but you're still using it by using, let's say, that's through GIS. What we try to do in GIS, it tries to provide huge amount of spatial database and temporal database in a collated manner so that you can try to integrate multiple sources of information, spatial as well as temporal, and integrate and try to analyze them together, which is typically done by a civil engineering profession people for a long time. We used to call them as draftsmen earlier, and then we used to call them as cartographers afterwards. Okay. Are people basically who prepare the maps for us. Okay. That's done physically because of their artistic skills, and the same thing is now done through GIS. So what a cartographer or a draftsman was doing traditionally in civil engineering profession is now being done through GIS. And I want to talk about GIS. Very simple to say that give me any feature on a surface. Okay, any feature. It can either be represented as a point, line, or polygon. Okay. So, for example, if you have, let's say, Survey of India benchmark, or a rain gauge station, or railway station, bus stand, etc. Okay. So all of them are simply points. So you can just try to specify what are its coordinates, maybe XY coordinates, or latitude and longitude, and that's how identify that point. Or you can have a line. I said line, but it looked like a curve here. Okay, these are segments of straight lines which are all put together to prepare a curve like this. Okay. So you can have as many number of line segments as you want to prepare a curve like this. That's another feature. You can show it for river, road network, rail network, etc. And then polygon means an area, okay, like a lake. Okay. Then or watershed, like Mangalore city outline or Karnataka state outline. Okay, such things are polygon. The only main difference between line and a polygon or an area is that in case of line, the starting point and ending point are different. Whereas in case of polygon, the point where you started, that's the place where you end up. Therefore, you close it. Okay, so it becomes a polygon. Right? So any feature, give me any feature, we can try to represent as point, line, or polygon. Just to drive that point home, here I'm showing a geospatial database, a set of basically compatible data layers or themes. The first layer that you're seeing, all these layers, you're seeing 5 layers here, all these 5 layers belong to the same region, in the same scale, or same spatial resolution. Right? Then what you are seeing, the first portion, first layer is actually land use polygon. Means, for example, this is, let us say, an urban area, this is a water body, and there is parks, and there is an industrial area. Like this, there are different polygons, and all these polygons are put in one layer. And over that layer, now we can put one more layer saying soil type. Maybe some portion is black cotton soil, some is silty soil, etc. Okay, so these are different soil type polygons. So both are actually polygons. Then if you look at the third layer, okay, it's showing a stream, and on that is one yellow dot, one gauge station, another gauge station, etc. And that is point information. And the stream itself okay, is a line information. And then watershed boundaries, this is one sub-watershed, this is another sub-watershed, etc. These are all polygons. So you have multiple layers of the same region put together. And the simplest question that you may want to ask, for example, is that in the urban area, tell me how many number of stream gauges are there passing through that urban area. Okay? Then you can try to answer that question by this map. Together, you can try to find out where are the stream gauges located. So within this portion, if there is any stream gauge, you could count them and you are trying to answer that. So that is called query-based analysis in GIS, and which we can do very easily, seamlessly, by having as many number of layers as possible. Again, I refer to the draftsman. Draftsman, what he used to do is, he used to prepare them in a transparent sheets or tracing sheets, right? Same thing now in the computer system, they are all put one over the other in any particular order. And GIS has been playing a very important role as far as water resource assessment or in general for natural resource assessment itself. I would put them in three major important. One stage is for database development, where you try to collate the data like the way I have just shown you, collecting, processing, and inventorying of hydrologic, hydroclimatic, hydrogeological, and auxiliary data. In this case, you may have some data which may be at one point, for example, the rain gauge is recording rainfall, and it is recording rainfall for, let us say, daily for 20 years. So 20 into 365 points of data will be there at that location. That's a temporal database attributed to one point within the map. Okay. So you keep collecting all the data and try to put them in multiple layers of information. Then the next stage is to talk about extracting some technical information. For example, in our BTech hydrology course, when there are so many number of rain gauges within a basin or within a region, if you want to find out the representative rainfall, we try to draw Thiessen polygons or ISO heights and to find out what is the representative rainfall corresponding to all those rain gauges together. That interpretation of data, spatial as well as temporal data, by hydrologic modeling, regionalization, etc., can be done through GIS. So we can do modeling of data, topological modeling, network modeling, cartographic modeling, and map overlay, extraction of geostatistics, etc., can be done in this second stage. And third stage is the more important or final output, like the way you are seeing in your Google map, etc., is knowledge extraction or knowledge dissemination. So here what happens is all the interpretation that is done through GIS is made able to the user in a very user-friendly manner with a very good GUI, graphic user interface. Okay, so data technical information are converted to knowledge for decision making by the decision maker. He may be simply an user, Prime Minister of India, or any particular concerned ministry, things of that kind. So for them to visualize and take decision, we can try to provide the information. So GIS, all these three important aspects. And we have been using extensively GIS for better assessing the water resources in a basin. The third tool that I want to talk to you briefly is called, this is called a digital elevation model. Again, this is also very traditionally known to all civil engineers from the time immemorial. Only thing is that, we are trying to do it in computer nowadays. If you are, let us say, having elevation data using, let's say, dumpy level, what you do, you put a staff gauge somewhere and try to get the elevation of it. And, from that you try to get its reduced level, or you also try to get its level with respect to mean sea level using a benchmark as a reference, right? So when we do that, that means what? We have the elevation of that location. And that location is specified with respect to XY coordinates, or latitude and longitude, right? So at that point, we have the elevation information, and we also know its spatial coordinates. Let us say that we try to store it now on the computer. So that elevation data becomes digital elevation data. And then we try to play around with the digital elevation data using some computer programs or algorithms. It becomes digital elevation modeling. So that's what we do as far as digital elevation modeling is concerned. And what you are seeing here is almost like a three-dimensional view. This is a very popular red color line that you are seeing here, which is referred to in surveying terminology as a ridge line. Means basically a contour joining the points of highest elevation around the region. Okay, and you can also see a brown line here, which is actually referred to as a valley line, which is actually the line joining the points of lowest elevation in that region. So water flows through this, and this would become, the red line would become kind of a boundary for your watershed or the basin. Okay, so such things can be easily visualized with the help of digital elevation data and by playing around with that. So, what is done is that, if you have X coordinate and Y coordinate, and for every X and Y coordinates, if you try to put the elevation as Z coordinate, okay, then you can see this kind of boxes that are constructed, okay, showing the points of high elevation and points of low elevation. Instead of having this kind of boxes shown here, okay, if we try to join a smooth curve using by interpolation, by spline or any other approach, okay, then we can try to generate a smooth surface like this. Okay, so you can see a peak here, we can see a peak here, we can see a valley here, and by the elevation data and the topographic information that is there on that region. If it is steep, it will have a different type of runoff, and if it is flat, it will have one. And then it also depends on how the stream network is connected, and all those aspects can be estimated very nicely using digital elevation data. We have the digital elevation data, from that we can derive all this information. I request your 5 to 8 minutes of concentration to make you familiarize with all these tools. Okay, just takes 5 minutes or so. We start with a simple classroom problem like this. What you're seeing is simply a 3x3 box. Okay, let's say at the center of this box, we have put our staff gauge and measured the elevation there. Okay, and the elevation there is 67. It may be with respect to mean sea level, 67 meters. Okay, now this box size itself is, let's say, 1 unit. That 1 unit may be, let's say, 100 meters by 100 meters, or 1 kilometer by 1 kilometer, or simply 1 meter by 1 meter. Whatever the way, you have collected the data for this 3x3. So it is simply 3 units by 3 units in length and width, right? And for that box, for every box center, we have got the elevation data. That's the first thing. And that means box size is uniform. Therefore, we also know what is the size or the length between two boxes. Now, as you can make out, this is 67, this is 56, and this is 44. That means when compared to this point, this is at a very low elevation. And when compared to this point is at a much lower elevation. And when compared to this point is at a much higher elevation. So what we can also do is that, standing here, try to find out what is the slope in this direction. What is the slope? Slope is nothing but the elevation difference by the distance, right? So the elevation difference is 67 minus 56. And for example, in this direction, if you want to find out 67 minus 53, by the distance is 1 unit. Therefore, 67 minus 53 by 1. That is, slope is 14%, if you like. In this direction. And if you want to find out in this direction, what we will do, 67 minus 44 is the elevation difference, but the distance is actually a diagonal. That means, the horizontal distance is 1 unit, vertical distance is also 1 unit. So if you want to find out this distance, use your Pythagoras theorem, and square root of 1 square plus 1 square, that is square root of 2. So 67 minus 44 by square root of 2, you see the slope of 16.26. So from this point, we can find out the slope in this direction, and from this point, we can find out the slope in this direction, and in this direction. And to be generic, let us say we are standing here. We can find out the slope in 8 possible directions, right? Find out the slope in all the 8 possible directions. And among them, some may be upward slopes and some may be downward slope. For example, this is an upward slope and this is a downward slope. This is also a downward slope. Now, among the downward slopes, identify the one which is the steepest downward slope direction among those 8 possible directions. Right? And if the soil here is saturated and if a rainfall occurs here, water will move in that direction. Means water will try to move in the steepest downward slope direction. So what happens then? This point, from this point, try to indicate in which direction water would move. Okay, this will be the direction. Okay, so put an arrow here in this direction. Like that, do it for every box or every pixel. Okay, assuming that the border that we are seeing here is actually a ridge line. That means it's a higher elevation. So water cannot flow out of it. Okay? So with that assumption, you try to put arrows for each box. That means what? If occurs here and the soil is saturated, water would move in this direction. So what happened? From the elevation information, now we got the flow direction map for every pixel. Okay. Assuming that the concept is very clear to you now, I will extend the size of the box from 3 by 3 to 5 by 5. Okay. And I'm showing simply the arrows. These arrows are indicating the steepest downward slope direction. Okay, so if water falls here, it will flow in this direction. And if water falls here, flows in this direction. Then what? You try to connect these arrows. Okay, water falling here will come here. And from here, it will go here. And from here, it will go here. So try to put all these arrows connected. Then what happens? You have the flow path. From flow direction, we got the flow path. Okay, and we also got the flow network because, if you want to consider this is a very large area, let us say that one box itself is indicating 10 kilometers by 10 kilometers. Okay, then it's a very large basin. So this may be one tributary, and this may be another tributary, and this is the main course of the river. This entire basin is draining at this place, okay? Mouth of the basin, right? So that's the simplest concept. From elevation data, we can talk about flow direction, flow path, and flow network. We can also then ask a question like, how many cells are contributing to this location? Okay, and there are a large number of cells or grid points which are contributing to this location when compared to this. Here only 3 points are contributing, right? Therefore, the stream or the discharge flowing here will be much less when compared to the discharge that is flowing here. The stream size, its width or its depth can also be estimated because of the number of contributing cells to that location. So some watershed area and things of that can be identified. So in a nutshell, what I said, it can be explained here. We start with elevation data, 5 by 5 box, okay, and we found the flow directions, and flow directions we got the flow path, okay, and from flow path we can try to ask questions like how many cells are contributing, flow accumulation grid, okay, 1 cell here and 2 cells, 8 cells here, 20 cells here, 24 cells here, etc. So total the 25 cells are there. All 25 cells are contributing here. This size is different from this area is different from this area. Okay. So then you got this, and you can also put a question like this is a GIS based query. Then tell me those points which are having at least 2 cells contributing to that location. Then the posts that are shown in blue color are the ones which are having 2 or more, so not at least 2, more than 2 cells. Okay, so these are the areas that are shown. In the same way, we can show this as the mainstream, and we can show these as substreams or tributaries. And you can also see that the contributing area, okay, is also shown in different colors here. So this is one sub-watershed area, this is one sub-watershed area, this is one sub-watershed area. All that is done through digital elevation modeling. As using simple algorithm, this algorithm itself is called D8 algorithm because there are 8 directions in which water can flow from a given location. Okay, so using this idea, if you are given a large basin, okay, you don't even know where is the basin boundary. Simply take, let's say, Karnataka map, and you want to identify different rivers and their sub-basins. You can do it using D8 algorithm. Okay, And that's the way we can try to estimate the complete watershed boundary. And once you know that the box size, for example, this box size is, let's say, 1 kilometer by 1 kilometer, is 1 square kilometer. So count the number of boxes: 1, 2, 3, 4, 5, 6, 7, 8. So 8 boxes are in one color. So the watershed area of that color is 8 square kilometers, right? So multiply the spatial resolution at the number of boxes, you know the total area or sub area of each watershed. That's the way we can try to use DEM extensively for many information. And then we can also talk about drainage density, stream order, and many other aspects can be derived using this concept of D8 algorithm. That's the main important use of DEM. And where do we get this DEM data? I mean, if you have patience, take some this dumpy level and go around and do it at total station. Otherwise, remote sensing itself can help us to get the digital elevation data. There are many techniques through which we try to get the elevation data of a given region. And the one that I'm showing here is not from satellite, but from a space shuttle Endeavour. Okay? And this is called Shuttle Radar Topography Mission. And through that, using a technique called radar interferometry, we got the elevation data for entire globe using this mission. It's a one-time mission, sometime in 2000. And this elevation data is available for the entire globe at a very fine spatial resolution. And it depends on the latitude. For our country, it is available anywhere from 80-meter resolution to 100-meter resolution. Okay. And nowadays, we are also getting the interpolated product at 30-meter spatial resolution. So for every 30-meter by 30-meter box of the entire country, we have the elevation information available from this source. This is not the only source. If you try to use Corpusat DEM, there also you can get it. Or if you try to use Aster DEM, you can get it from that satellite, like that. Multiple sources are there. Now, I try to use the data, and this is actually for Karnataka portion of Krishna River Basin. And if you try to overlay on this, the SRTM DEM data, it will look like this. It looks like a very innocent black and white or grayscale image. Okay, but what you are seeing here at every location is the digital elevation in gray tones. Okay, black indicating very high and white indicating very low elevation, and that's depending on the scale that you adopted. Now, let us try to look at for the entire Krishna Basin itself, which comprises of Karnataka, Maharashtra, Telangana, and Andhra Pradesh. Okay, so for this entire basin, please remember the shape of this basin. And if you use the SRTM data and the D8 algorithm that I have mentioned to you, then you derive the drainage pattern. The drainage pattern looks so dense, it almost looks like you don't see any drainage pattern. I refer to it in my class as African hairstyle. If you just zoom red box here, okay, you can see a drainage pattern now. And if you try to further zoom into the small red box again, you can see detailed drainage pattern. Actually, they're all straight lines. If you recall flow path and flow direction that we have done, they're all straight lines. And all those straight line segments are joined together to provide this kind of stream network. Okay, that's the way we can try to derive detailed drainage map for a given region of our interest. It may be for a small urban area, or for the entire continent like Africa. You can try to derive this. Now, with the help of these three important tools, remote sensing, GIS, and DEM, if you try to impart logic model, okay, then we can try to get the best of all these tools to model our hydrology and assess the water sources in a much better fashion. And for that, the last tool that I want to talk to you itself is a very big tool called AV-SWAT. SWAT is a soil and water assessment tool, okay, and it's a physically based hydrologic model, and that too grid based. That's one advantage because of the way we try to get the remote sensing data, okay, and it is open source software. Therefore, if you want to use it, you can download that software and use it, or the codes themselves are available in Fortran. You can try to manipulate the code and modify it, adapt it to your own requirements. That's why it has become popular, although I'm not campaigning for it. And this SWAT model, when it is floated on a GIS platform called ArcView, it is called AV SWAT or RPU SWAT. Similar thing is also done with the QGIS and many other GIS platforms. So basically, the SWAT model is the heart of it, okay? And there is a very good front end as well as back end for this. So front end may have DEM sources and remote sensing sources for land use, land cover, and a temporal database like rain gauge data or stream gauge data, etc. So all these are made available through this GIS platform and try to provide the inputs that are required like DH algorithm, etc. We try to use them to give the inputs for the SWAT model. What it requires is subwatersheds. And subwatersheds are further subdivided into what are known as HRUs or hydrologic response units. Okay. And they can be very neatly delineated with the help of DEM, land use, land cover, and hydrography maps. And that becomes a very important input for the SWAT model. So I try to demonstrate that with help of one major river basin or portion of a river basin of Krishna called Malaprabha Basin. And Malaprabha Basin in itself is about 2,500 square kilometers, okay, which looks like a small portion on Karnataka map, okay, and that's the area that we are referring to. And I request you to now remember this shape. It is actually part of Krishna River Basin. Remember this shape, okay. And here, what are the pink dots that you are seeing are the places where we have the rain gauges. So, like with the way I mentioned to you, we drew decent polygons to estimate representative rainfall using GIS, okay. And we use a lot of information on this basin, like maximum minimum temperature, wind speed, relative humidity, solar radiation, etc. And all this data was collated into GIS platform and was used in AV SWAT framework. Okay. So now I'll quickly run through the tools that we have talked about. This is actually remote sensing data, satellite data. IRS list 3 data and panchromatic data were merged together to create land use, land cover map of Malaprabha Basin. And these are the categories under which this entire area is categorized into different land use and land cover. And this is a map that is again derived from the soil map, okay, mixed clay, loamy, spherical loamy, etc. Okay, so these are the different types of soil classes that are derived from remote sensing, but is also verified from other source that is available like NBSS and LUP. Then this is our SRTM DEM data. And here the DEM data is shown in different colors for different elevation ranges. Okay. You can see this is a valley portion and the blue line is actually the ridge line. Right? So using that, we can try to derive a complete drainage pattern for this basin using the D8 algorithm that I have just specified. Okay. So this is the drainage pattern that is derived for this basin. And once we do that, we can also talk about flow accumulation, right? So this is a place where a lot of water is getting collected. Means all the water that is falling here is getting poured into this point. That's why it is also called pour point in SWAT terminology. And there is another pour point. There is another pour point. Finally, all this water will flow into this location. And this is a place where there is a Malaprabha Dam. Looking at the entire basin, but up to Malaprabha Dam site. Okay. So this is a place where the water is getting collected, and this is a place where we have the inflow data available, which stream flow from this entire basin. Okay. So that is the data that was used to calibrate this entire model for this basin. Okay. So this is our drainage pattern derived. And from this, you can put your 4 points like this and try to divide this into as many number of subwatersheds as you want. Okay. If you want, this itself can be one subwatershed, this could be one subwatershed, etc. Or put them together and call them as a bigger watershed. Like this, we can try to put different subwatersheds. Okay. And all this is done through GIS. So what we can always do is we can overlay as many numbers of layers of information as you wish. So on this, right now we are seeing some watersheds, but on this we can also put our drainage network. Okay, then you can see in each subwatershed how is the drainage network. Okay, and on this you can also put your pour points, so you can estimate the point of the importance of pour point is that in the SWAT model, at that point you can estimate what is the runoff. And at this point, what is the runoff? Like this, for every pour point, you can, for example, let's say you want to construct a small dam or a check dam here. What you can do, you can impose a pour point in your SWAT. Then it tries to give you what is the flow that you can expect at this point, and what is the volume of flow that you can expect at this point. Therefore, you can decide your check dam capacity and things of that kind. Like that, we can try to estimate the flows at any location and finally calibrate it for this particular location, because this is the only location where we have the data available. If we have multiple locations, of course, it's much better. Then, if you try to look at the land use land cover, by pixels or spatial resolution of the satellite, we can try to find out what is the area. So in subbasin 1, how much area is under pasture, water body, urban area, forest, agriculture, etc., as far as the land use is concerned. And in the same way, for soil type, how much is under clay type, loamy, skeletal clay, etc. And that is for subbasin 1, subbasin 2, subbasin 3. Like that, for every subbasin, we can try to find out what is the different land use land cover, so what is the soil type. And if you recall, Soil Conservation Service curve number method, SCS curve number method, okay, what we require is the land use, soil type, and the AMC, antecedent moisture condition. Using them, we can try to convert the rainfall into runoff. That's what SWAT will do. Okay, in SWAT, SCS curve number approach and the corresponding tables in detail are implemented. Okay, so it tries to estimate the runoff from it. Okay, and it also tries to estimate what is the lateral flow, what is the groundwater contribution, what is the percolation, what is the vapor transpiration, using all the methods that you know. For example, Feynman-Pontiac method can be used for evapotranspiration, or Hay-Grace method can be used to estimate evapotranspiration. And all such things are implemented in SWAT. That's all. Okay. So for every period, we are trying to estimate for the given rainfall, what is the surface flow, what is the lateral flow, what is the groundwater component, any percolation, evapotranspiration, etc. Okay. So that's the way we try to estimate. And once we estimate, we compare that flow with what is actually observed at the outlet. Okay. And if they compare well, it is good. If they don't compare well, we try to fine-tune the parameters of the SWAT model until the flows are comparing well with the observed flow. That is what is known as calibration of the hydrologic model. And after the calibration, we try to use some other portion of the data for validation. And if the validation is also good, that means the model is ready for that basin. And it's also ready with a very good confidence levels, like R square is 0.95, which is very good. Then we can try to assess the water sources of the basin for the future periods. You just give me the rainfall, I should be able to give you the water available in that period. So that's what we try to do with all these tools. Water source assessment in a river basin. That's the main aspect that we can try to do with all these three important tools. And once we do that, once we know that in the Malaprabha Dam, for example, we are getting so much of water in every period, every day or every month, okay, then how best to utilize that water? Reservoir operation planning can be done with this input. So water resource planning and management for various purposes like irrigation, hydropower, for industrial requirement, domestic use, etc., can all be planned based on the water resource that we have assessed. Okay. So to do that, these are some of the very useful tools. Image processing, remote sensory data, and DEM and GIS will play a very important role to assess water sources of a given basin. And before I conclude, I just want to say that this is a scope for future research in this domain. I had talked about remote sensing, basically optical remote sensing, but when compared to that, if we try to use microwave remote sensing, we can get images of a given region even during cloudy conditions, because if there are clouds, we don't get any area or information below that, whereas microwave will help you. And if you want to segregate different types of vegetation species, it is not possible using multispectral data. You may not be able to differentiate between sorghum and maize crop. Whereas if you try to use hyperspectral data, we will be able to do it. So there is scope for it. And India has recently launched one hyperspectral remote sensing satellite called HISIS, but there is a lot of scope for this to develop. As a matter of fact, 3 of my PhD students are working on that now. And synergy of multispectral multi-day data is very, very useful concept, including microwave and hyperspectral. And challenges in DEM, I have given a very nice DEM picture here, but there are some challenges come with multiple sources. There is something like DEM, DTM, DSM, etc. And to distinguish them and try to do very well in each of these domains is a challenge, but it's something that is achievable. And finally, with all these tools available, we can try to talk about impact of climate change on water resources. As a matter of fact, the student who has done PhD here, Anandi, she studied on impact of climate change on water resources of Malaprabha River Basin. And if we try to float that into a decision support system like Google Map or Google Earth Engine, then we have people sitting in different locations can interact with each other using this DSS platform and take decisions for the river basin planning and management. That's what I wanted to say. I'm done, and if there is a time, I will be able to take questions.
Thank you very much, sir. Thank you for the nice presentation. So there are few questions raised by the researcher.
Yeah.
Can I read it out, sir?
Sure.
What is the accuracy of DEM?
Okay, that's a good question. It depends on the source. If you are, for example, using SRTM DEM data, its accuracy ranges anywhere from plus or minus 5 meters. Okay. Whereas if you try to use Cartosat DEM, which is commercially, we have to buy it. Okay, and if you can buy it, it is available at a 5-meter spatial resolution. There you have very fine spatial accuracy. You can talk about less than 1 meter accuracy also, plus or minus 1 meter elevation difference. Okay. That's the accuracy that we can get depending on the source that we are looking at. And if you are looking at ASCER DEM data, it is again, accuracy is not that precise for urban modeling, whereas it is very good for river basin modeling. And if you are looking for very high accurate data, especially for urban setup, like Chennai, Bangalore, etc., Bangalore, then what we can do is we can go for another technique of getting DEM data that is called LiDAR. And if you use it, especially if you use ground-based LiDAR, okay, then we can get the elevation information at a very fine accuracy of a few centimeters. And it depends, but it's a very expensive proposition because LiDAR survey for a given city is very expensive. For Chennai, after Chennai floods, it is done. Like that, for a portion of Bangalore, it is done. And IISc campus, we got it done. Like that, in some portions, we are doing it, but we get very fine accuracy through that data. So it depends on the data source. The accuracy of DEM depends on the data source.
Thank you, sir. One more question from Dr. Radhakrishnan K, Professor Civil Engineering Department in MMIT.
Yeah.
How best we can use the DEM-based GIS analysis and 4-point grid division in river regeneration and recharging the aquifer?
Wow, beautiful. I would say that in both those places, river regeneration as well as recharge location identification, etc., DEM can play a very important role. Okay. Only thing that we need to do is that DEM database that we are acquiring should be of relatively recent origin. SRTM is good, but remember, SRTM is of the year 2000. Okay. Whereas if you try to use ASTER DEM, it's a satellite-based DEM, okay, or Cartosat DEM, you get most recent digital elevation data of that region. So use that to identify the pore points, and then you try to identify locations where you can put check dams, or you can talk about river regeneration, or if the river itself has changed its morphology, it's meandering. Okay, then those aspects can also be derived through DEM. Only thing that I suggest is look for very fine and recent DEM database. It can play a very important role.
Well, there is one more question.
Yeah.
How to account a subsurface flow in the particular SWAT model?
Yeah, that's a good question in the sense that, although SWAT is considered as a universal model, everyone is using it extensively. SWAT has some limitations in modeling subsurface flow. It divides the entire subsurface region into very small segments, okay, just 3 or 4 segments, and that creates a huge problem in proper groundwater assessment. There is no issue as far as lateral flow and percolation modeling is concerned in SWAT. Only problem is what happens if it goes below that. Okay, for the deeper layers, the groundwater movement is not properly done in SWAT, especially if you're talking about places where we have lift irrigation happening. We pump the water from a deep well, which is a few tens or hundreds of meters below the ground. And that portion is not properly accounted in SWAT model. So what people are doing, and we also have done some work, and if you see my website, you can notice, is that if we have that kind of deep groundwater body interactions, then SWAT model can be tweaked by merging SWAT model with a model like ModFlow, which is basically good for groundwater contribution. And that will be dealing with groundwater contribution, and SWAT will be dealing with surface water contribution. And they both will be merged together to model the groundwater contribution much better. So there are some tools which are available now to do groundwater contribution assessment much better when compared to what a typical standalone SWAT model can do. So it's possible. You can do it with the help of integrating it with a very good groundwater model. If you are not interested in ModFlow, you yourself can write brief equations to model the aquifer in the region and integrate it with SWAT. That's what we have done for the Malaprabha Basin itself to talk about the lift irrigation activity that is taking place in Malaprabha. That is there in my website.
Thank you, sir. Last question we can take up.
Yeah.
How this DEM can be used for lichet studies?
I'm not sure. It depends on, lichet basically happens in where we are talking about solid waste dumping and etc. And for the dump yard, a lichet movement will take place. So what needs to be done here is that as we are dumping a solid waste in a dump yard or in a location, it looks like a mound now in places like Delhi and other places. Okay, so in such places, the topography of that small region, the dump yard, changes as we keep on dumping. And depending on that, we can try to continuously upgrade our DEM database. And then we can talk about the water movement from the solid into it, in through it, and then lichet movement. It can play a role, but it is more governed by how frequently we are updating our DEM database itself, because the DEM is changing day by day in that location. So if that is properly taken into account, or if it is properly modeled, you don't have to actually get the data, but you can also model the elevation changes. And then you can talk about lichet movement. That's the way you can try to use DEM as a tool to assess or to basically ascertain the lichet movement.
Thank you, sir. Now I would like to take the question from those who are present in this particular session. If any questions, Uday Kumar sir.
Sir, it was a very good presentation. I really enjoyed it, the way you presented so beautifully, the concepts and all. Of course, even a new comer who does not know about these basics. So I would like to preserve the presentation. So that was my opinion. Thank you very much for the nice presentation.
You're most welcome. Thank you.
If there are no questions, we can.
Sir, Dr. Nagesh. Yeah, thank you very much, sir, for your nice presentation. Basically, I am not familiar with remote sensing and GIS, but I know I have completed one fundamentals of FPTL course on remote sensing and GIS.
Okay.
Sir, you told something about the elevation, where what we are doing manually or through the theodolite or dumpy level, the contour line and finding the elevation. And if you are doing through GIS, what is the accuracy of that?
Yeah, it actually depends again on the source of data itself. If the source of data is available at a very fine grid scale, then the accuracy will be very good. But instead, if it is a very coarse grid, for example, let us say for your own college campus, if you are trying to estimate the contours or draw the contours, then if we have the data at a very 100 meter by 100 meter grid box, then we get one scale of contours. But the same region, for every 10 meter by 10 meter box, if we have the elevation data available, then we can draw the contours much more finer.
That
That's
means
why
if that pixel is smaller size, you will get more accurate.
exactly. That's
Yeah.
right. Yeah.
Okay, sir. Thank you. Thank you very much.
Sir, you gave a very informative lecture, and I had some doubts on Pixel. That also you have cleared very well. And
Thank you.
basics you have explained, sir. Thank you.
Thank you very much. Thanks a lot.
Good lectures. Thank you.
Thank you. Thank you.
Thank you, sir. So we came at the end of the session, the conclusion. Thank you for the nice presentation, sir. The presentation covered all the aspects of remote sensing and GIS with the introduction, also deep images, and it was also covered the land use, land cover, the processing of the images, how this particular digital elevation model works, and finally the SWOT models and application of the particular SWOT model for the estimation of runoff and all. So it covered all the aspects of a particular water resource and remote sensing applications. So thank you very much for accepting our invitation, sir. On behalf of the Department of Civil Engineering and NMMIT NIT and CTCS Organizing Committee, I thank you, sir.
Thank you very much. I am so happy to be part of this, and I felt happy to interact with all your distinguished colleagues. And I wish you all the best for the remaining part of the conference, and hearty congratulations to you for organizing